So this is all about witnessing quantum gravity effects, and I think most of the participants of your meeting are probably familiar with quite a lot of stuff. What I will do effectively is summarize the main idea, and then I'm going to summarize a few experiments that I think are interesting enough to consider, and probably I won't have much more time than that. Can you see this? Is this okay?
Yes. Yes.
Perfect, great. So witnessing quantum gravity. So basically, I think most of you will know that the argument is that you are using two quantum probes. So you have a quantum system and another quantum system, and somehow the idea is that they couple individually. So again, the key assumption is that they separately interact with the system that you're trying to probe here. And I'm putting a question mark because we're asking what kind of properties this system has. And basically, if these two quantum probes, at the end of these local interactions, so to speak, if they end up in an entangled state, then you can put forward an argument that this really says that the system in the middle that's being probed has to have some quantum features. And now, of course, how much you can really conclude depends on what kind of additional assumptions you make. There are all sorts of intuitions that you will read about in the literature, and I think they probably immediately spring to mind when you think about these things. I think the paper by Sugato and his colleagues would be using something that we call LOCC, local operations and classical communication. So when they're thinking about it, they're thinking about a field. This could be any field, of course. I think it's exciting to apply it to gravity because we know the least about gravity in the quantum sense. But basically, it applies to any really field or any other system that couples in this way. So the way they would think about it is that if you believe that the field couples locally to the masses, so each of these masses initially just sees the field in its own vicinity, then basically that's effectively something that we call a local operation. And we know that local operations cannot increase entanglement in quantum information, which means that if you start with no entanglement, if you start in a product state of the two quantum systems, and if you end up with an entangled state at the end of it, that can only really be that whatever channel in between exists cannot be LOCC, cannot be just local operations and classical communication. And I think it's very fruitful to think about it in terms of information theory. In fact, when Chiara and I thought about it, I think we came from two very different angles. I worked a lot on various correlations in quantum mechanics, and she came with her own ideas from constructor theory. And actually, in constructor theory, they are defining information in terms of computations. So it's very interesting because you take computation as the primary notion, and then you divide what you mean by information from that. And somehow when we met in the middle, these kind of arguments we saw could be made in a much more general way than assuming quantum mechanics and assuming decohering channels and so on. So I just want to alert you to this fact that it's a very, very generic argument that you can make in this case. Another intuition that you might want to have is simply that you can think of the two quantum systems as doing a measurement of temporal correlations on this intermediate system. So you can think of the first interaction as measuring, let's say, Z observable on this system, and the second interaction happening later in that frame and measuring again another observable, let's say X or Z. So effectively, the computation of entanglement between the two quantum systems is completely tantamount to violating Legge-Garg inequality on this intermediate system. So the intuition really is that two-point spatial correlations on two separated systems, in fact, in this case, correspond to temporal correlations. And therefore, if you get 2√2, if you like, it does inequalities between these two quantum systems, that effectively suggests that the system in the middle really has complementary degrees of freedom. It has to violate the Legge-Garg inequality. So these kind of arguments are very intuitive, and they're kind of very clear to anyone who comes from foundations of quantum mechanics. Anyway, I don't want to bore you too much with this, because I want to say something about the experiments that can be suggested. So basically, as you know, these two systems, the two quantum systems, have to be able to exhibit, of course, the full quantum behavior. You're really assuming that they're equivalent of a qubit or more than a qubit if you think about higher dimensionality. And so what you really have to ultimately do, as you know, is some kind of make a superposition of these masses, then make some kind of interferometric experiment with each of the masses. And ultimately, this allows you to measure various observables and therefore various correlations between these observables. And I think if you take one, I don't remember last time I counted this, but if you take one of those optics books like Born and Wolf, I think last time I counted something like 17 different interferometers. I'm sure there are more, you know, it's an old book. So basically, as you know, you can think of this as a Mach-Zehnder interferometer or Michelson interferometer. Any interferometer will do the job. And the first one that Chiara and I had in mind, and I think it's very similar to what Sugato and his colleagues had in mind, is simply to simply split each of these masses into a superposed state of two different locations, and then again use the fact that gravitational interaction between two branches that are closer to each other is somehow stronger than the interaction between these other branches. In fact, I think if you set this up properly, you can even completely ignore this these other three branches. You can assume that they're equally weak. And what happens then is that ultimately your state of two masses that starts in a completely disentangled state of each mass being in its own superposition, what happens ultimately is that for the right timing here, which is a function, of course, of the distance and the masses as well, you will end up with a state that's actually a maximally entangled state, where the minus sign, this would be the full pi phase shift, if you like, that's obtained when you wait for the exact amount of time for this interference. And somehow, I think what surprised everyone in this case is that, you know, the experiments seem to be very challenging, but these masses don't really seem that far out of the reach of current technologies. So we are certainly talking about masses that are smaller than Planck's mass by 6, 7, 8 orders of magnitude. But on the other hand, of course, we are still talking about masses that are definitely 5 or 6 orders of magnitude or more bigger than the diffraction experiments with matter waves that various people do, like Marcus Arndt and others. So somehow this is one of these interferometers that you can think about. And I want to make a very quick comment before I tell you about a few other ideas. I'm effectively, I think, summarizing 5 or 6 different papers that Chiara and I have either published or on archive, and I think you can find them very easily. The comment I want to make is that if you, of course, what's exciting for us to explore is to ask what are the degrees of freedom that are non-commuting, in this case, if you really have gravitational field in mind. like I said, the argument here is completely general, and you can think of this intermediate system as anything. And in fact, we've written papers about various physical, even biological, macroscopic systems that we would like to probe in this way. But if you're really thinking about the gravitational field, and if you follow this analogy with in the linear regime with the electromagnetic field, then I think what this would imply is that the electric-like and the magnetic-like components of the gravitational field would be the two non-commuting degrees of freedom. So I think the argument would be very similar to all of these arguments due to Landau, Piles, Bohr, Rosenfeld, all of these guys. I think anyone familiar with field theory will know these arguments. And I think these are people who were struggling to understand the quantization of the electromagnetic field. And they had all sorts of thought experiments about why you wouldn't be able to measure the electric and the magnetic field simultaneously. And it always boils down to having a test charge on which you would have to measure the position and the momentum simultaneously. So somehow the argument says that if you could measure the E and the B field components to an arbitrary accuracy, then of course you would also be able to violate the ordinary uncertainty principle on a charge. And I think the argument would be identical here as far as the gravitational field. I think what's interesting, as far as I'm aware, the magnetic-like component of the gravitational field has actually never been tested, even in its own right, classically speaking. So I think this would be interesting. I might be completely wrong about this, but this is what I recall from reading various literature. Anyhow, here you could, so if you, of course, if you commit yourself to a model, and this seems to me the most sensible model in this regime, then you could even comment on what exactly are the degrees of freedom of the field that don't commute. Now I want to say a couple of more things that I think are interesting. One of them is a different kind of interferometer. Like I said, you know, there are 17 different interferometers, and any one of them, of course, relies on adding amplitudes up and taking the mod square of that to get the probability. So basically, they all rely on quantum effects completely. What's interesting is that here we are talking about spatial superposition. And somehow, whenever you talk about collapse theories and all sorts of alternative models, usually you're thinking about space. I think this seems to be, I actually, you know, it seems to be a natural basis in which things should collapse. Whether this is fundamental or not, I think is anybody's guess. It's related to the kind of basis problem in many worlds and all of these other things. But anyhow, what I want to say is that if you think a bit more broadly about this, then instead of having two masses in a spatial configuration superposed across two different arms of two interferometers, you can actually think about two masses, each of which is localized, but in fact each of them is in a superposition of different masses. And I think basically double beta decay comes to mind immediately. This was something that David Deutsch told me about when I was discussing. I had something completely different in mind, actually. I had two Bose condensates in mind, and each of them would be in a superposition of a ground state and an excited state. And as you know, higher energy just simply means more massive according to relativity. And if you could put each of these masses in a superposition of two different energy states, you would actually get exactly the same scenario as here. So instead of, I'm going to write down, instead of having a superposition spatially of two different spatial locations, you would simply have two particles, each of them would be in two different massive states. And I think I was a little bit disappointed because when you do the calculation, even with the largest condensate that people make, I don't know, assume something like 1 billion atoms. I think even that's a stretch. Then the gravitational interact, if you think about all the billion atoms in the ground state, and at the same time all the billion atoms in the excited state, a bit like a GHZ state of each of these, then you could run exactly the same argument. You could entangle these Bose condensates. But I think even this most optimistic scenario is still not massive enough for us to see any significant phase. So we are orders and orders of magnitude from where we would need to be. And I think the same can be said about the beta decay. The only hope I had there, maybe, of course, we're talking about particles that are extremely light, but the interference they undergo stretches over much bigger distances than what we would naturally do in the lab on an optical table. So I was hoping that if this beta decay happens spontaneously, double beta decay, and it unfolds the interference over very large distances, then maybe the phase could build up. But I think a very quick calculation shows that this is, of course, also not very strong. So ultimately, for you to end up in a state that's a maximally entangled state of this kind would take a lot of time. And the minus sign here too, M2. So basically, you can think about two spatially interfering objects. You can think about objects that are localized in space, but they are really superposed as far as their energies are concerned, or masses, if you like to think of it like that. So these are two different kind of interferometers that we have in mind. Of course, like I said, there are many others, and the question is just if there is a suitable way of getting all of these numbers right so that we can really test this. What I want to say now is this latest, and I think it features in the title of this. So I'm going to erase this just to be able to show you what I have in mind. So this one is interesting to me because I think there is a lot of discussion, and actually with Chiara and I put this paper out on Friday, and I think already by the end of Friday we had 3 or 4 comments from various people in the community, because I think the question whether equivalence principle holds in quantum mechanics is an old question, and I think there are probably countless papers written on this topic. But the question really is interesting because you could, instead of using gravity, you could use what people call the Sagnac interferometer. So let me just write Sagnac interferometer, which I kind of discovered by chance when I thought I invented it myself, which was quite funny. I discovered it when I worked on geometrical phases. And I thought this is very interesting because if you spin your interferometer, you're going to get an extra phase there, which is exactly the kind of a Haranoff bomb equivalent, if you like, in optics. And then one of my PhD students actually told me at the time that I was very foolish. I was something like 100 years out of date, and told me that there is an interferometer called Sagnac. So basically this guy is like your standard interferometer. You can think of it like a Mach Zehnder interferometer. And of course it's traditionally done with classical optics. But I'm going to talk about matter waves because, as we know, the description is exactly the same. In fact, the mathematics turns out to be exactly the same. So you're going to have a mass that undergoes, splits at the first beam splitter, and then it's recombined, and then you measure the interference pattern at the end. But the twist in this story is that this is mounted on a spinning table. So basically the interference is measured while this disk is spinning with a certain angular frequency omega. And this is interesting because this introduces an extra phase shift in this case. I think there are lots of, by the way, you could have gone down the fits-all interferometer. There are many interferometers that would actually have a very similar idea behind them in some sense, how to introduce the extra phase shift between two arms. And now what's interesting is that you get an extra phase between the arm 1 and 2. I'm going to write it just as e to the I phi. And this phi is something like m over h bar times omega times area. And the reason why I remember this, the reason why I remember the formula is because it's very easy to remember. But the reason is that it looks extremely suggestive that this is a kind of a Harmer-Bohm effect. And I think most of you will probably know this, that you can think of the frequency omega as a kind of effective magnetic field in this case. It's going to be important for what I have to say next, because magnetic field is a kind of curvature. And of course I want to think in terms of relativity in this case, which is going to be the punchline. So you can think of omega as the magnetic field. A is the area of your interferometer. M is the mass of the particle that undergoes interference. So it's a very simple formula, actually. And what's interesting now is that you could be thinking about a situation that only involves acceleration due to this spinning disk, and there is no other gravitational, there's no gravitational field, if you like, there at all. But as you know, because of the equivalence principle, this is equivalent to having a gravitational field. In fact, most of you again would probably know that you can write a metric just as you would for curved space, and you could write it in terms of the radius of this interferometer and the angular frequency. So you can write a g nu that would capture completely this. And if you're in the limit of very, very small deviation from flat metric, then, as you know, you could write this as Minkowski plus this extra perturbation field. And you can do the calculation exactly the same way that you would do in linear gravity. You could now couple this h to t mu nu, and you could write down a Hamiltonian for this process. And in fact, if you solve the dynamics with that Hamiltonian, you will get exactly the Sagnac phase that I wrote down. And so now let me run a thought experiment by you, which I find extremely interesting. And I don't know what to conclude about it myself. I think it's an interesting question to ponder. And it is related to the meaning of the equivalence principle. I have my own bias about it, and I'm happy to comment on it as well. But let me tell you what you could do here. You could take a single mass at radius r1 from the center, and you could simply do the interference where this mass goes in two different paths, clockwise and counterclockwise, and then it interferes at this point. So the mass enters here, splits, and then you measure the interference here. This would be your standard Sagnac. Now imagine on top of it that you have another radius, R2, where you can also do interference. So now what I'm describing is an acceleration equivalent interferometer to two masses being coupled to the gravitational field. The only interesting thing here is that there is only one mass involved now. And so what I have in mind is the following. I want to split this mass so that it does interfere at two different radii, while the disk is spinning at a superposition of two different angular frequencies. So I'm not just going to have one omega, I'm going to put omega 1 plus omega 2. And this is very interesting because what happens now, so now I'm thinking about 1 degree of freedom being the distance from the center of rotation, and the other degree of freedom being the angular frequency of this disk rotating. And what happens now is that you're ultimately going to end up with a state where your radius, your spatial position, gets maximally entangled to your angular frequency. So you're going to start in a state where you are superposed at two different radii, and you have a superposition of two different angular frequencies. And if you time this interference appropriately, so that this phase ends up being equal to pi, now I'm going to have two different areas, and I'm going to have two different omegas. So there are 4 different phases, exactly as I have in the gravitational case. This is going to end up being R1 omega 1, R1 omega 2, plus R2 omega 1, plus R minus R2 omega 2. So you get exactly the maximally entangled state that we had in the gravitational case. The difference, the big difference, is that we are talking about a single particle and 2 different degrees of freedom of this particle, namely R, the radial position, and the angular frequency of this. So it's quite interesting that if you believe in the equivalence principle of this kind, then the entanglement generated here would tell you that the gravitational field is quantum mechanical, even though there is no gravitational field, so to speak. It's all about rotations. But because we know that acceleration in this case is indistinguishable from gravity, we somehow believe that this also would be a proof of the quantum nature of gravity. And I think this to me sounds very interesting. It's not even clear what exactly propagates in what way in this interferometer. How do I now take into account the locality that's very important in this case? I think there are a number of interesting questions that I can think of, but I'm simply running this by you as another possible interferometer that doesn't have to rely directly on gravity, but could simply utilize the equivalence principle. I have a lot more that I could say about it, but I'm just going to stop here, and maybe if there are questions, I'm very happy to answer them. Thank you.
So, yes, but maybe come here to ask the question so that he can...
Where should I speak?
There is fine.
Okay, so Marco here. So my question is the following. It's related to the application of the equivalence principle. So the equivalence principle tells you that acceleration is locally indistinguishable from gravitational field. The keyword being locally. So you're making a non-local experiment here. You have something that is extended in space. Interferometry is in general extended in space. So I don't see this being a property of the gravitational field in any sense, because if you want to, I mean, the non-locally, if you make a non-local experiment, you can distinguish acceleration from gravity. Gravity is an effect of curvature, while here you're all the time working in flat space-time. So there are no gravitational degrees of freedom being involved here. So how do you why do you want to interpret this as a gravitational as an effect for
Yes,
quantum
I mean,
gravity.
you're absolutely right that I understand the question. It's a very good point. And in fact, when you have a superposition, I think I would think of the equivalence principle as holding in each of the branches of the superposition. So just think about the way we think about any conservation law in physics. You know, you're basically saying that it holds in each of the branches if you're talking about a superposed state. So a bit like, you know, if you like the many worlds interpretation, it would say in each world, classical world in a superposition, equivalence principle holds. So what this means, if you have an extended superposition, is that you can gauge away gravity in one location, but you can't gauge it away in both locations simultaneously. And in fact, that's exactly what the phase built up between these two branches shows you, that you cannot simultaneously. I think this is a direct consequence. This is not in contradiction with equivalence. This is the equivalence principle.
Okay, we'll have to think about that more.
Yeah, I don't know if it makes any sense what I'm saying. Yes. Actually, I had a comment from Lucian, who I think has his own way of thinking about the equivalence principle, and I think his comment said that he thinks that what we proposed is exactly what he has in mind. It's just that I tried to look at his papers and I think I need a bit more time. I think he has a very different terminology and approach to this. But somehow the claim is that it also boils down to thinking about different states and different branches separately, and the equivalence holding in each of them, but certainly not globally across all of them.
Okay. Is there another question? No? Should we wrap it up?
Just one comment. The gravitational part of the... can you hear me?
Yes, very well.
The gravitational part of the magnetic field, the magnetic part of the gravitational field that was measured by gravity probe B, by Lanczos. There are measurements, all right?
There are measurements. Okay, I would be very curious because I've talked to people who are planning some of these experiments, and somehow they were saying that they are very challenging.
They were challenging. Gravity probe B was horrendously hard, and it lasted.
That would be great
for
to
years and
yeah,
years. But they had measured it, and then Ciufolini independently measured it with Lanczos, with the laser tracking satellite.
Great.
So it's, there is more than one now evidence of the magnetic part of the gravitational.
Yes, I also thought it would be something that's more likely to come from astrophysics side of things than from the lab based. I think in the lab I couldn't find anything.
No, in the lab, no. It's 1 over c
Yes.
square with g over c square, so it's very small.
Yes.
This is what you're talking about is very challenging conceptually, and I was trying to think about. I think it has to do with the talk you probably couldn't hear the previous talk, because this changing reference frame and viewing the effect as either in g mu nu or it seems that there should be a way of thinking it in terms of using different degrees of freedom for describing the same physics.
Yes.
So I think it's related somehow to the kind of thing that you guys were talking about before. If I had more time to focus, probably I could say something more clearly. So conceptually, it's very one wants to think about that. Now, I think, suppose you could do that. I mean, I don't know how you would put a rotating thing in superposition, but suppose I think it would be less convincing as an argument that gravity is quantized for the reason that is pretty obvious. I mean, it says, because it would be easier to think it not in gravitational terms.
Yes, I agree.
In a sense, your other experiment survives if c goes to infinity. This survives if g goes to 0.
Yes.
Which is sort of stronger as
yes, I agree.
So maybe hi, Vladko.
Hi.
Maybe I just can comment on this relevance of quantum reference frames. So in this Giacomini et al. Paper, we actually formulated the equivalence principle for the Newtonian gravity. And if you think about that, an accelerated observer that observes a free particle will effectively see a Newtonian gravity in the Schrödinger equations, then you can extend this and think about superposition of accelerations, and then what you will see that the g, which we small g if it is on Earth, will become an operator. So what a particle will feel as if it were in a superposition of gravitational field. So it indeed is kind of agree with what Vladko said, that and can be formalized within the quantum reference frames, at least in the Newtonian league.
Yes.
Is there, Andre, do you want to ask something? Come here.
Oh, no, it was just a clarification, because you said there is only one particle doing interference, but it's getting entangled with the motion of the whole.
Absolutely. This is what gets. Think about it like this. Think about an electron in the hydrogen atom, and you now superpose it across two different principal numbers. But in each of these numbers, you superpose it across two different angular states as well. So you're superposing n as well as L at the same time. That's basically what I have in mind. You're absolutely right. There's only one particle that undergoes this interference, but it goes through two different interferometers at the same time. That's what's interesting. And it's much easier if you think of an atom, because of course then we are used to superposing all of these quantum numbers. If you have something more macroscopic in mind, then I really think it's a very challenging experiment indeed.
Okay, thanks.
Okay, we're just on time. Thank you very much, Vladko.
Thanks a lot. Enjoy the rest of the